As mentioned earlier, we require a separate video to explain the concept of cross-entropy as a loss function. First, let's understand what entropy is. This is a four-sided die. The die is fair, with an equal probability for all sides being up. When the probability distribution is uneven, the die is considered biased. Let's play a game with the die where one person rolls it and the other person guesses the outcome by asking yes or no questions to narrow down the possibilities until he knows the answer. We will explore different probability distributions and questioning strategies. In strategy 1, the first question is it 1 or 2? If the answer is yes, we ask the second question, is it 1? Regardless of the answer, we can determine the outcome in 2 questions. Therefore, this strategy always requires 2 questions to reach the result. In strategy 2, the first question is it 1? The second question is it 2? The third question is it 3? We can define a function to return the number of questions for the answer. Pause the video to check strategy 3. Now let's define a function that rolls the die 1,000,000 times and calculates the average number of questions required to reach the answers. The function takes parameters such as the number of sides, probabilities, and questioning strategies. The variable count accumulates the total number of questions asked in the 1,000,000 rolls. Face represents a random number selected from the available sides, based on the given probability distribution. The questioning strategy can be either strategy 2 or strategy 3. After 1,000,000 iterations, the function computes and returns the average number of questions required. For strategy 1, the average number of questions is always 2 regardless of the probability distribution used. We then call the function for strategies 2 and 3, and display the results. Various probability distributions are tested. Running the code may yield slightly different results each time. It is unnecessary to rely on simulations to determine the number of questions needed for strategies 2 and 3. Let's consider the second probability distribution as an example to illustrate this. For a large number of rolls, such as n equals 1,000,000, the distribution indicates that half of the rolls show side 1, a quarter show side 2, and 1/8 show sides 3 and 4 each. Based on the questioning strategy where sides 1, 2, 3, and 4 require 1, 2, 3, and 3 questions respectively, we can calculate the average number of questions to be 1.75 for strategy 2. You can pause the video to understand how the average number of questions is computed using strategy 3. This is the formal definition of Shannon entropy. We can calculate entropy manually or with a short code. Let's compare the results of our guessing game with the entropy. For prob 1 and prob 2, the average number of questions matches the calculated entropy values. The strategies used to achieve these values divide the yes and no answers equally. For prob 3 and prob 4, we cannot find a way to divide the binary answers equally. In these cases, Shannon entropy serves as a lower bound on the average number of questions or bits needed to identify the value of the roll. While many people associate entropy with information, they are not the same. Entropy quantifies the amount of missing information required for a complete probabilistic description of a system. Specifically, it represents the average number of binary questions needed in an optimal decision strategy to determine the specific outcome based on the probability distribution. Essentially, the less information we have, the more questions we need to ask to find the answer. In the case of uniform distributions, more questions need to be asked.